Begin the session. Good evening to one and all. I am Anjali Chaturvedi, a sophomore at IIIT Allahabad, and I welcome you all to eSummit 2021, a techno-industrial fair. We have amazing sessions lined up for all of you. A classical computation is like a solo voice, one line of pure tunes succeeding each other. A quantum computation is like a symphony, many lines of tunes interfering with one another. This was said by Seth Lloyd. The mixing of complex spectacles like quantum with something as necessary as coding and computers has opened a new sphere full of possibilities and opportunities. Quantum computing is the trending technology which, in spite of being under development, has shown tremendous potential. So for the quantum computing panel discussion, we have as today's moderator, Professor Shayan S. Garani, Associate Professor at Indian Institute of Science, Director, Physical Nano Memories, Signal and Information Lab. To share with us more, we have Mr. Manas Mukharjee, who is the Principal Investigator in the Department of Physics at CQT in NUS. Building a strong community of women in quantum computing, we have Nithyasri ma'am, CEO and founder at SheQuantum. One of the leading organizations when it comes to quantum sciences is IBM. And thus, we also invite Shesha sir, who is the quantum computing expert at IBM. Yes, sir, we might start now.
Okay. So thank you for the nice introduction, Anjali, and it's a pleasure to have a distinguished set of panelists here. We have Manas, we have Shesha Raghunathan, and we have Nithyasri here. So welcome all to the panelists, and thanks a lot to IIIT Prayagraj for arranging this and getting us all aboard on this platform. Okay, so welcome one and all to this panel. So we are living in today's age of electronics and sort of moving on and embarking on to the AI age, and AI / connecting to the quantum age. And we are thinking about bio-inspired systems, robots, which can emulate biological activities. For example, if we think about bots that can go like snakes and potentially, useful for our defense applications and so on. Or be it engineering, silicon cochlea, and these type of things which can be implanted fold back into biology, right? These are different kinds of applications one can think of, and we are really at that age and sort of moving into quantum. And how can quantum and AI come together, right? And one side is deep down quantum physics and quantum information and everything else. And another side is AI, which you're learning the environment, you're adapting, and then you're bringing these things together. I mean, how can we think about the confluence of AI and quantum? So it's where this speed matters. Can we think of really exponential speed up in the way we can learn environment, we can adapt, and we can make decisions through potentially quantum systems that go hand in hand with AI, right? Do we have the right kind of materials? Do we have the right kind of experiments? And where are we heading? These are questions that come naturally to a scientist's mind. And there's also the business side of things, trying to connect with the industry and technology and manpower and everything else. So it is with this perspective I would like to bring in this panel. So I would like to introduce you to the panelists. Manas is an associate professor. His director is associated with his principal investigator with the Center for Quantum Technologies at National University of Singapore. We have Shesha Raghunathan. He's a distinguished ambassador at IBM research. I think sort of moving from the system side of things into quantum. Maybe you start off with the quantum, perhaps to start with Todbrun. Am I right? And then we have Nithyasri Srivathsan, who is an entrepreneur and a she entrepreneur, quote unquote, which is going to possibly encourage a lot of women, not only embarking in science and technology, but also going on the entrepreneurship ladder. So this is interesting. So with this introduction, so let me begin this panel. So the way we will do is we go about with a brief introduction into quantum computing. I just would like to sort of brief up, and then we'll ask the panelists to voice their opinion where this technology is heading, and we'll take some questions going around the table, and then there will be specific questions to the panelists in their areas of expertise, and we would like to hear from them all. So things have been making waves in the quantum segment, quantum computing, with the 53-qubit quantum superconducting engine that we have from companies such as IBM, Google, Rigetti, and others. And then this notion of quantum internet that is picking up. And recently China had this interesting thing that they developed, and they showed and demonstrated that you could communicate across space and stuff. And these have gone beyond the normal QKD, which we have been talking about since last 2 decades or so. Okay, so we are interested in basically transforming the landscape of today's classical computing and communication systems to what we call embarking into the quantum space, quantum communications leading to quantum internet, quantum computing, which can potentially supplement classical computing and maybe take over in certain applications which are really demanding for the same. So with this, I would like to go around the table to the panelists. So we'll go all the way from academia, industry, and entrepreneurship. I mean, we'll go through the cycle because this is where we need this kind of synergy. So first question is to Manas Mukharjee. Manas, where are we on the quantum landscape from experimental and technology perspective? And I would like to also know your opinion with respect to the NISQ perspective and long-term needs, and also maybe talk about a little bit global versus the Indian perspective. I mean, in theory, we are we are already making we have made a significant leap in terms of algorithms and things like these. We are looking at fault-tolerant systems and stuff like this. So, what is your opinion on the quantum landscape? And then going forward through NISQ and the fault-tolerant computing sort of that setup, and then your perspectives, global versus local. Yeah, the floor is yours, Manas.
Thanks, Shayan. Okay, so I think if I understand the question is first about what are the different possibilities in quantum computing, particularly in terms of the hardware. And that, of course, is a very open question. I would not say that there is only one winner in this case. Yeah, the landscape is very open, and that's makes it so exciting because you have possibility to play it even among. However, I mean, as of now, there are two most advanced ones. One is the superconducting circuits, as you mentioned. The other one is ion trap, which did not mention. But the difference between these, or let's say complementarity of these two, are if you look carefully into it, speed is one thing where the superconducting qubits are much faster compared to the ions. However, if you look at the long coherence time, the atoms are really long coherence time. If you look at fidelities, the atomic fidelities are way better compared to this superconducting one. And there is a natural reason for that, because atoms are used as clocks, which is the best known precision that you can get from. So, and that's the reason behind that. Now, one could also think of hybrid systems of these, and that's also coming up in the horizon. So not only just have superconducting circuits, but you can also make superconducting circuits hybrid with quantum dots, or atoms with superconducting circuits and things like that. So the field is pretty open, and there are some of these objects which are far from being a quantum computer or quantum processor in any way, but they have a lot of promise. For example, the One is where Microsoft is putting money in, is the topologically protected materials. But again, there is not even a single qubit, so it's very hard to say where the field is. Yeah. The other possibility is silicon defects, where Australia has put a lot of money in, right, and Microsoft as well in that. But then again, the good thing is that we know a lot about silicon. The bad thing is that we can't make the best silicon as of now. Yeah. So meaning impurities in silicon spoil the game. Yeah. So in a way, there are many opportunities. Now coming back to the case where India is,
in a nutshell, you're saying that it depends. You mentioned about these hybrid schemes, and what we would like to understand is it depends on the application, right? For example, these defect systems, the NB centers, and these defect systems, essentially, you think it could be useful for metrology applications, sensing metrology applications, and where do you see this perspective with ion traps and superconducting qubits? Where do you see this hybrid system sort of?
Yeah, okay. I was restricting myself to computing only, right? Because I think we have to be very careful on this, because as the introduction was mentioning, QKD has nothing to do with computing. It's not even quantum communication. QKD is just the way to send the keys, and after that you do encryption and talk by a classical channel. So that's something one has to be very, very clear about. So if we restrict ourselves to only computing, then where the hybrid system comes is that if you think of it, the ions or atoms in general are very good memories. So if you do a computation with a superconducting circuit in a very short time, you can think of actually, if you can couple it to an ion, you can store the quantum state of it and then reuse it afterwards. Now, this is not a state of the art that you can use it in scaling up, but these are things which are being researched for the next generation, and you are expected to see some of these distributed computing coming in. And that can only happen if you have nodes which can store quantum memory, act as a quantum memory, which then can be read out. So quickly going back to your second kind of thoughts, right? So about the kind of global scenario versus Indian landscape. In the hardware side, I think there has been a very big jump in terms of funding, at least, right? Which was done a couple of years back with the Quest program, and now with the Quantum Mission. I don't know whether the money has been disbursed for Quantum Mission, but those are really nice initiatives to start with, to get to the gear to where the rest of the world is. But looking at the global landscape, of course, this is a race, right? If you think of it, it's a race. It's the same race as there was for the other things like moon or even the atomic bombs, right? On the two good and bad sides of things, yeah. But you can't deny it, for any country would like to take advantage of this, and that's what is going on. Having said that, I think it is not yet this stage set for stopping collaboration, because this is a hard subject, yeah, for anyone, for any individual, for any country. I mean, so therefore, from academics, we do really see that certain things are narrowing down with some restrictions coming in on export control and things like that, but that's not really good for the field itself over longer run. Hoping that these things would not take a major step, it would come back into normalcy.
Sure. So I would like to thanks a lot, Manas, for this summary from the academician's side. So I would like to hear from Shesha, Raghunathan, on this. You've been with IBM. You've possibly seen the evolution of IBM. I think they pioneered early data storage systems, you know, and I worked in data storage quite a bit, almost for a decade and a half. I'm still working on, along with my other areas. So what are your perspectives, you know, putting forth from the industry side? You know, you have one side in quantum memories, and people are talking about these systems, and then coupling this with computing and communications and all that. So where are we on the quantum landscape? And what do you see are the directions from an NISQ perspective, noisy intermediate scale quantum systems, to long-term needs? and your perspectives in the local, Indian perspective versus where it stands globally.
Thanks, Shayan. Thanks for the opportunity. Thanks for IIIT Allahabad for inviting me here. I think I'll echo some of things that Manas just mentioned in terms of if you start from the lowest level, which is the hardware, and let's work our way upwards. Hardware, there are two front runners, as Manas mentioned, ion trap and superconducting qubits. Those are the current front runners, but from the looks of it, they are front runners, but not clear winners at this time. We don't yet know what technology will win eventually in terms of things. From industry standpoint, technology has to have the scalability aspect. What will scale much, and which will, much like the way transistor happened. If you look back our history and journey through our classical hardware till where we are, you can see the journey has not been a single thing. There have been multiple waves that have come with different jumping technology. The initial transistor design that was done, then you had a bipolar in 70s, and then you had a field effect coming in 80s and late 90s, and then CMOS getting into the 90s, and then silicon on insulator, and then you have FinFETs. There have been waves of technology that have come and that have pushed that along. But then the core transistor technology of how to design a transistor in principle has remained, but the way that is silicon based, the way you do it, different variations of those technologies have come over a period of time. Right now, I think we are a little bit pre that era this time in terms of solidifying which way to go at this point in time. As I mentioned, the clear front runners are these two technologies at this point. Different companies are betting on different technologies, predominantly on superconducting qubit for good reasons. One of them being that it is based on silicon technology and the fabrication technology. We have gotten a lot of insights and expertise over the past 50 years plus of silicon hardware development. There is a lot more advancement that has happened in that technology that we leverage on. And the model, the superconducting qubit model that we currently have leverages that fabrication technology, and therefore, and also it is in the similar pattern of developing a processor like a classical hardware that we do. So there are certain benefits to it. The next,
and PV is, for example, most of the superconducting things is based on cryogenics, and see that's a difficult part. And do you think this is going to scale up? And do you think we need some room temperature based superconductivity? And where are we in that direction?
So I'll get to that. So there are a few, even before that, even within this technology, the other question will be is the reason why the classical hardware took off was the large-scale integration capability. We could squeeze the transistor, generation on generation on generation. We could reduce the size of the transistor and therefore increase the amount of transistors we could get in a given chip dimension. So if you look at it, the similar argument of what superconducting qubit, for example, what will be the miniaturization version of it? How will it scale as you reduce this size of it? Can it still be as effective? What is the model? I think some of the things will be of active research at this time. So that's one angle. Within this technology, there will be a push to obviously miniaturize. That's the only way to scale out. To increase the number of qubits per unit dimension. And then how do you integrate, etc. That will be on that. The temperature part of it, it really, so there are few technologies that are being explored, be it photonics or NV center, those things that work in room temperature or near room temperature. There will always be, in terms of industry adoption, in the large-scale industry adoption, the scalability question will always come in. How do I manufacture at scale will always be a question. And as I said,
so what are your perspectives? Where are we? I mean,
currently, still, I think superconducting qubit still is where the industry would be at this time because of It's sitting
in research stage yet, right?
We are not in the stage yet. As I said, it's still not a clear winner as such, but we are not at a stage where you would start thinking about when to switch type question, if at all. I think there will be, superconducting qubit is showing a lot of promise at this time. If there is some significant roadblock that comes about, then at that time there may be a shift, or if there is some other movement on one of the other competitive technologies that comes about and shows significant promise that is of scale, then there will be a shift. The industry will move accordingly. But at this time, my personal opinion is superconducting qubit is where we're going to be. There is a competitor, as I mentioned, Honeywell and others are in ion trap based things that will move on. Both of them, they have chosen a track, they're going to go after it. We'll push the envelope as much as possible, and then we'll wait and see how things proceed.
The answer may be both, essentially, because like the way you have hybrid systems like SSDs and HDDs sitting together on these hybrid systems, and possibly you may see a mixture of both of these technologies.
And I think that is at the lowest level, right? So I was going to go to the next level. There is a systems engineering problem too, in terms of coming to your NISC question. So these qubits that we currently have, at least let me constrain myself to superconducting qubits so that most of my comments are related to that. It is still noisy. It is not at that level of fidelity that you would need to do a fault-tolerant type quality, which means that as the hardware is evolving, what can we do to get maximum out of this technology? How best can we leverage this technology? And that's where the layer on top of the core hardware comes in. There are many compiler, transpiler type problems. That is, take the big problem. How do I maximize the use of this thing? Is where a lot of benefits are coming in terms of let us be more smart about how we use this qubit, because not all qubit are exactly the same. They have different noise profiles. The different connections have different noise profiles, and also in the case of superconducting qubit, there is a limitation in terms of connectivity, and there are some other constraints that come in. So leveraging that most effectively seems to be one avenue where there is some level of
so systems that at least in the next 4 to 5 years we are still in this NISQ stage, right? And before we actually
we are likely to be in that stage. And that leads to the next question, the other kind of hybrid. This is more at systems level hybrid compute comes in. The other direction where things are evolving in terms of hybrid computing is that computing at classical and quantum together as an algorithm. An algorithm that spans classical and quantum. I think that's another direction where recently there is a lot of results that are coming through that you're less likely to have the whole algorithm run on fully quantum hardware. More benefit, at least in the NISQ era, at least, is where you identify kernels of the compute that are harder to do or where quantum can do efficiently, map that over to quantum and have classical do its business. And then some classical compute closer to the quantum hardware to do some control mechanics is also going to be needed. But essentially, in a larger picture, at an application level, the kind of things we are seeing is a hybrid compute model, hybrid in the sense of classical versus quantum working together jointly. And those are the kind of algorithms where there seems to be some promise and a lot of work is happening around that.
In interest of time, I would like to switch to the next panelist. Thank you, Shesha, for a lot of these interesting discussions. So,
Shayan, may I shortly jump in just to clarify, right? We were asking about scaling down in size, right?
Yes.
But if we look into just classical computing these days, if you look at the heavy computing, right, you don't do it on your desktop or it's all in cloud, right? So why do you bother about, and quantum particularly will not do the same thing as classical doing. There's a specialized computing anyway. So everything can be at one given place and you are only accessing it by cloud. And that's the architecture we're looking at.
Yeah, this is very interesting. This is where I think communications and computing getting together might be the right paradigm for this. I mean, we're talking about really harnessing entanglement, doing teleportation and all these things. And that's the key to be able to have these communicating nodes, distributed, you have these computing nodes that are distributed that work on teleportation-based, computing framework, and we also have communications across these in a way that they can share information. And I think that seems truly how we are sort of poised, moving from the classical distributed framework on to towards the quantum thing. So it's a very good perspective. Yeah, thanks, Manas. Nithyasri, what are your perspectives from the entrepreneur side of things, where we are in the quantum landscape, specifically from the Indian context and globally, and what you think are the imminent challenges for NISQ realization within India?
Firstly, thank you, Professor Shayan, and I'm very happy to be part of this panel. Thank you, IIIT, for having me here. And yes, to answer the question, I'm the CEO and founder of SheQuantum, and what we do is to bring in more women into quantum computing, give them simplified education, and then push them to follow research, internship, and job opportunities. That's what we do. And essentially what I do is to inspire more women to take up this field, because I think one of the most important challenges that quantum computing faces is the lack of women representation. And of course, I do think that there should be more women. In general, to talk about the NISQ part of your question, I think it boils down to scalability. Of course, we want more effective fault-tolerant computers. But the question then scales again to, do we have a very qualified human resource to do that? So that is where it's very important for people to know that such and such a field exists, and that it is simple. The thing about quantum computing is that it's in general, popular science articles, what is projected is that, hey, this is a very disruptive technology that is going to crack your RSA course. We are not still there. It's a very relatively young field with many open questions and many open answers as well, which are looking for questions to be found. So I think that the problem I see is that we need more people to take this up. We need more people to educate simply, and we need more people to learn it properly. So, of course, IBM is doing a lot in this. They're providing trainings in Qiskit, especially the framework that is used for software in quantum computing for building algorithms. What I saw is that when I was talking to Scott Crowder one day, and he was telling me that there are a lot of open resources in quantum computing. There are a lot of takers too. But the problem is they are not qualified to take up a job or to do research in this field. So I think that's where the change should come. And me personally, being a woman, I feel that the change should come from the women. And yes, I feel that we have a long way to go, but we can do this if we are together. And that is what SheQuantum also aims to do: inspire, educate, and then give you an opportunity, and thus making anybody and everybody being able to contribute to this field. And one very important point here is that this field is very interdisciplinary, and that is the beauty of this field. You can be a physicist, you can be a mathematician, you can be even a financial analyst, you can be a biologist, and you can still contribute to this field. And of course, seeing of real-life applications, I would say drug discovery, which comes from biology and intersects with quantum computing in a very beautiful way. And so is finding new chemical compounds using quantum chemistry and algorithms together. I feel that that kind of an application should come in. The academia and the industry together should be able to, influence people to learn theoretical knowledge, to gain theoretical knowledge as well as hands-on experience, and then they go together, and more women representation, and we will definitely see success in this and scale.
Great. I mean, so what you're saying through is you're kind of acting as an interface and bridge between academia and industry and stuff, and then sort of, and also evolving this essentially in your own niche.
Absolutely.
I'll get you a specific question on that note. So let me just go through one round of quick questions again from the panelists, and then we go to specific questions. So back again to Manas. Manas, what technology do you think is the most promising to appear first, and what's the time frame? We discussed it at a very high level. We had a general round, but now coming specifically, now we are talking about be it ion traps or superconducting stuff, or maybe the quantum communications beyond the QKD, right? So which technology do you think is going to be the first, and what is the time frame you think? Can you tell me in like a couple of minutes?
So is it related to computing, or is it related to technologies in general?
It could be your favorite technological field. I mean, what you're working on. So you think you're working on ion traps? I mean, it could be a broad perspective. If you honestly feel that superconducting technology is there and it's going to be there very soon into products, I would like to hear that. Or maybe you say, yeah, it could be just quantum communications to start with, all realizing something like this, or maybe ion traps. So I just want to know your perspective, which technology you think is going to be making the headway first, and when you think it's going to be.
Right. So if I understand the question correctly, it's first of all, there are two granularity here. First thing is which technology is the low-hanging fruit to really be translated to real use, right? And if and from quantum, and that I think we have no ambiguity. Everyone knows this. So QKD is already deployed. So there is nothing much in that. So you see space to ground communication. You see already land to land communication. You see fiber communication. It is deployed. So that's the if you think of it, that's there is no ambiguity in here. Now, if you think of the next generation of things, I am more or less certain that it is going to be sensors, another technology which is which shows a lot of promising things right now. I mean, just for example, magnetometry or gravitometers. These are like very, very competitive as compared to the classical ones. So that is a matter of time when they will ones. I mean, we should not undermine the classical knowledge in sensing, which is very, very strong. I mean, so going beyond that is possible and doable, and probably that's going to happen next. And then the third question is,
you think it's sensing. You mentioned about sensing, this gravimeters, the magnetometers and stuff. What is the time frame we are talking about? A year, 2 years?
1 to 2 years. I mean, some of them are already there. So 1 to 2 years is good enough. I mean, already you see gravimeters are very competitive with the gravimeters which are classical. And the only difference is that even if you use a classical one, the drift is large. So if you cannot run it for a very long time. So which means you have to, while the quantum are very stable because it's an atom, it doesn't change with time. So what you do, you calibrate your classical one once in a while, in 12 hours or so, you calibrate it. So it is already deployed in some sense, if you think of it. The other thing is magnetometers, right? So squid-based magnetometers were there for brain imaging, for example. But then again, they are huge, and you need a full fridge on the backside of it, right? So they are being replaced by RFS. So these are the atomic-based magnetometers, and they run at room temperatures, as sensitive as that of the squids. So those are the things which are more or less, you can think of it, they're already deployed, more or less. Then I think would be the last to come is going to be more disruptive. This is natural. So the quantum computing would be very, very disruptive. And as Nithyasri was telling, right? So it is, the thing is, it's computing at the end, right? So you're computing something. So it has impact in every sphere of life. It doesn't matter what. So it will be your data. So for example, data science will be, and data science is everywhere. If you think of AI and ML, they are working now because the computations our computing power has grown up. If you look at the concept of AI and ML, I mean, this is there since 50s or 60s, but there were no computers available to use them. Now you have those powers, so you have it, right?
And all the things.
So now if you have quantum
computing directly, right, at a sensing level itself, you want to bring in these algorithms, right? AI and ML, and that's how you might want to.
So those are computing. Right. So those are. Yeah, those are happening in some way. So you are saying that those classical machine learning algorithms are already in use in optimizing sensors. Yeah. So those, I think, is a very low level of that. I mean, what we are going to see the cream is when you have quantum machine learning algorithms.
Yes, exactly.
So those are still futuristic, yeah. Or quantum AI. I mean, we don't talk about this. There are very vague concepts about that, but let's not talk about that, yeah. But classical machine learning is already in play. I mean, also IBM. I mean, Shesha would agree on that, right? IBM or any of these machines they have at the optimization level uses machine learning because that's the best alternative we have. Now coming back to the quantum computing, there comes, if I interpret your question rightly, you are talking about what would be the right choice of platform. I think we kind of agreed to disagree on that in a lot of senses, that there is no clear winner at this point. And there will be no clear winner in the next 5 years, because as Shesha was pointing, everyone is trying to push it to the level where it can be. Then there would be, I mean, in all of these technologies, we know beyond 100, and so you need some technological jump, meaning you have to change somehow to the conventional way of pushing the envelope. So, but till these 100, 150 or 200, let's say, yeah, qubits, you can do a lot of things. That's where it comes to. Now, the question is, how good are you in finding the right problem? And there is a big debate. And of course, the supremacies we see is, in a way, they are good to show off, but in a real sense, they have no meaning because you don't know where to apply them.
Okay, great. Thanks, Manas. What are your perspectives, Shesha, on this? So which technology is going to come first? And you are the industry person, you've been in the industry, and what are your perspectives? Which technology is going to come first, and what's the time frame that you're going to see this into a product that some of us could use? I mean, all of us could use.
Right. So I think by and large, I agree with Manas's gradation. Right. So one aspect of communication, QKD and those devices are already there. It's further along in terms of doing work. Sensing is the next logical thing to go. IIM's point of view is obviously compute, and more so putting things on cloud and doing compute there. So naturally, our interest is in the compute side of things. So there, I think naturally our focus will also be in the compute, and broadly the roadmap in terms of a breakthrough algorithm. So the interesting part here is the quantum hardware as of today in the NISQ era, and it's likely to be there for some time to come, is that it's noisy, and therefore we don't have the full power of quantum computing, if you see what I mean, because of the noise. Then you ask yourself, okay, if I cannot solve a general problem in a broader sense, can I solve point problems in a targeted sense that can provide value? Think of the ASICs that we used to have in 80s, 90s, and these things where you had hardware to do specific things. Like a co-processor used to be there. Now GPUs are there, which are doing some specific pointed things. So can we use this hardware, though universal in nature, but can we try to target a specific problem, and can we solve it at scale that no classical hardware can do? That's the goal, and that would be a real advantage. That's when you really should demonstrate.
Which Nithyasri mentioned, right? I mean, drug discovery and some of these type of problems. I mean, there are plenty of such grand problems. And what do you think is a grand problem?
So I think there are different gradations, types of problems. One is the sort of quote unquote simulation problem. That would be to simulate the physical things. So if you go back to the origin of quantum computer, it was about simulating physics. That was the origin of, at least the modern sense of quantum computer. When in the 81 conference and the subsequent one, when Feynman delivered the lecture, it was about, can we simulate quantum physics using quantum physics? Right? That was the idea. That was the basic idea. So that particular problem space seems a little bit more promising in that it is naturally sort of fits into this compute model, if you see what I'm saying. It becomes a mapping problem in terms of you have one way of describing a system, but you have to take that and map it to the other way of describing the quantum systems, underlying quantum physics is the same. It's just that the way systems are described is different, right? So if you have a good enough way to map this and do it efficiently, then you're probably going to have a higher chance of succeeding in a simulation problem. That is, simulating something. So some of the examples that she was citing, say drug discovery was one specific thing. But if I were to reduce it to a little lower level, some physical system, you're trying to simulate that. And that, if you want to simulate using a quantum computer, it seems a little bit more natural to do. And the odds are that those kind of problems are likely to succeed.
That the computing scalability, the NISQ should somehow, you should identify the right kind of problem that you could possibly do in the NISQ regime, and you need to have technology that is ready for that emulation platform, right? Simulation or emulation platform.
From an industry point of view, you would always think about, so right, I have a quantum system or any system that you have, you will always think about how can I productize it? That will be the natural question. So which means that I would want to be able to solve some problem of real interest to somebody so that I can deploy it for somebody to use it. Right? That would be a natural thing.
I understand that perspective, but very specifically to the technology, my question is very specific. What technology you think? I mean, if you were to solve this problem on drug discovery or
our current roadmap for at least the next 3 years to 5 years and ahead, we seem to be on the superconducting qubit technology. That's our roadmap. We have a roadmap. We think that's the way forward. We have a very well specified number of qubit. So now we already have 127 qubits, and then we have planning to get to 400 plus, and then 1000 plus in the 2-year time frame. So those roadmap is set for the next few years. Of course, if there is anything disruptive comes, all bets are off. But that aside, that's the roadmap we are on. And the other thing is that the compute power now that we can realize with the current hardware is also increasing. We understand the system as time progresses, we understand it better. One metric of measuring, which is the quantum volume of the capacity that we can leverage in the current hardware, it's increasing quite rapidly, even much faster than what we initially anticipated.
Shesha, to cut you short here. So we'll have to move to Nithyasri. Now, slightly different question, but on the same thread. So what are your perspectives in terms of the manpower industry? Because you were very specific about women empowerment and, women leading changes and then getting onto this technology. Now, we are, if you think about research side of things, it's not really, all the universities are majorly into quantum. I mean, there's buzz happening around. And what are your perspectives in terms of the right career path, career opportunities, and how this empowerment thing can happen, and how you envision these things? What is your roadmap?
So I think when you talk about the right career path, it boils down to 3 things. One is taking the academia, one is taking the industry, and the third one is most interesting, taking both together. So I feel that this field has a sea of opportunities lying out there to be exploited. And I think that what we have to do is to explore all of them so that you get a whole idea of how to theoretically implement it, and then go on to actually implement it. And here I would like to say that universities are playing a major role there, especially in the US. I would say what I'm seeing is that in the US they have it inculcated in their undergraduate curriculum as a very small module. Of course, that it should be scaled up again, I would say that, but they're doing a great job there. To mention a few, we have the Harvard Quantum Initiative, we have the Chicago Quantum Exchange, and when I move to this part of the world, in Asia, I'm seeing a lot of work being done in Singapore, and especially
which countries you see? Japan, South Korea, which places around in Asia, which countries specifically focusing on the quantum aspect? Can you elaborate on that?
Sure. I see that there's a lot of contribution from Singapore in terms of academia as well as software, and especially in terms of QKD to space, taking QKD to space. There are a couple of spin out startups from NUS. That's a very interesting thing that I've been exploring. Also, the kind of research that's being done in Tokyo, especially Tokyo, South Korea, they are doing a great job as well. And I feel then if you move again to the Europe part of it, I see Germany and Switzerland doing a lot of work in it. And one thing common to all of these countries I see is IBM. They are playing the major and the crucial role in all of this. And I might be a little bit biased there because when I started out my quantum journey, it was with IBM. So that's where I started my learning journey. So I feel that, the change will come across when women and girl students are, shown the aspect of scope and the perspective of this field in terms of curriculums, in terms of summer programs, which IBM, D-Wave are also doing some of them. I feel that what's being done in America, especially by NSF, the kind of they catch them young. They go to the K-12 level, which is our grade 12 level, and that's where they start teaching their students. And I think it's very important that one should not come to know that such and such a field exists only in masters or PhD degrees. It should happen younger, and that's what I think. Yeah, we should
And what is the perspective on the experimental part? I mean, see, quote unquote, still theory algorithms is slightly. Of course, it requires a lot of. There's an entry barrier also, right? But from the experimentation side, I mean, you should have these. It's not like taking a temperature sensor or taking some pressure sensor and integrating within an IoT framework, and that's not the way one can think. I mean, that is scalable, right? I mean, I can expect any K-12 student to be able to do this. This is very, very specific. We are talking about like, this ion trap experiments with ion traps or light matter interactions and stuff like this. So what are your perspectives? How to get this scaling up done? I mean, first of all, these experiments have to be conceived. Most major universities should be having these experimental facilities and centers where they can demonstrate in their open days, etc., and students to be enthused and then be able to participate, right? Like, a physics major student, or not just physics student, I mean, anybody, as you mentioned, right? Sciences, engineering, STEM should be able to do this. Of course, I am more open on both the sides, male, female, other gender, whatever, gender unbiased, quote unquote, that they've been all, you need all the players in the level ground. So what is your feel? How this should be done in the sense of getting this experimental? The key is experiments I see today, right? Because you need something to show and so that people can believe in that, and then that can scale up. So what are your perspectives to get that sort of revolutionized within the country? Maybe this applies to any other country. Yeah,
absolutely. I feel
how to go about it.
Right. So I think that I'm not telling that there aren't, but there should be more number of research programs at the undergraduate level wherein one can choose a mentor and work on a real life project. Let's say traveling on quantum computing, let's take that, to be able to actually see and kind of, let's say, being given the knowledge of how you can manipulate those qubits in the traps with the laser. And actually seeing it being done, I think that is one of the most wonderful things. And I can say, especially for the physics part of it, physics students, they can be very easily pushed into quantum computing, because they're definitely going to be good in quantum physics. So let's take them from a level of superposition and then entanglement, which are all abstract ideas, and let them perform experiments like spin, and then relating that to a qubit. So of course, the experimental part of it is pretty less, I feel, right now, and it can change only when universities give more research opportunities to all of the students without restriction.
Here, something to add here, Shesha?
Yeah, I will make one comment, and this is particularly relevant to India in the Indian context. Let's remember that India is a leader in IT sector worldwide.
Yes.
I think if I remember correctly, we employ something around 4 to 5 million if you include tertiary and other employment that comes around the IT sector. And I think something like $177 billion plus revenue or something growing is what we are generating from this space. Say in 2 to 3 years' time, and at least IBM's vision was to have some breakthrough algorithm come through that is deployed at scale at production in the next 2 to 3 years time frame. So then what's going to happen is that you're going to have obviously jobs coming through in the space of programming this quantum hardware. How do you program this hardware? So there, earlier when I talked about qubit roadmap, that was the hardware roadmap. I'll just make a comment on this software roadmap that may be relevant, more so in the Indian context. What we need to understand, as we see, there are 3 categories of gradation that we're going to see. One is, this is on the software side. See, once you have the assembly level language,
so I think it's more area of job creation process with a breakthrough technology, and the whole chain of manpower empowerment all the way. You have one leading technology which is
what happens is that if you have if you see the quantum space, you have the say Qiskit example. There is what is called as a QASM, which is a quantum assembly level language. So once you put the instruction out there, the hardware becomes, you can switch the hardware as it were. Then you have the software stack building on top. So there, I think there is opportunity to be had. There are different kinds of potential opportunities. For example, at least we see 3 categories of opportunities coming through. One at the lowest level is a kernel developer type thing, where you need to have a deep physics math background to be able to do certain sort of circuit level transformation of things. A level above that is you get these circuit kernels defined. You can do certain things efficiently and so forth. You think of it as, once you figure that out, the guy gives that as a black box. Then the algorithm guy pieces things together. And there, you probably need an advanced degree there in, say, computer science with some aspect of mathematics or physics, as the case may be. Then you have the application development. That's much more broader. And there, I think we shouldn't lose track of that, because not everything is at the lowest level where everybody needs to know physics, but there are different other things that are there where there is more opportunity that can come through, and students can prepare accordingly.
Shayan, we are really cutting off on time. We just have 5 minutes. So what I would like to do is, if there are any questions from the audience, we can you can please post these questions, right? If you have any specific questions to the panelists, you can please post these questions. Or if not, I mean, we can just collate all these questions together and we can email, and they can answer back specifically. That's also a good possibility. So what we just have 5 minutes. So I just want to kind of leave a minute for wrap up, but I have very specific pointed questions, from the panelists. So in a minute, if you could answer, Manas, what are the key needs for, basically, is there a way for academic research and bottlenecks faced in this area, and how can government industry come together to get lab science to the market, supporting blue sky research to technology? So what are your perspectives? Can you summarize just in a minute? We just have a minute. Yeah.
Well, I think it's pretty well known. There is nothing new in that. So one thing is, of course, there has to be sustained support from the government, because as we all know, this is still a very nascent field. Even though the hype is high, it's still a nascent field. Yeah. So you need a sustained. You can't do a knee-jerk effort like, okay, everyone is going ahead, let's put some money now. Yeah. You have to do it over the years and long time, and then also generate this manpower. I think that's a very important aspect, and India has that good manpower. So I think India can contribute into that. I would actually go a little bit more, a little bit differently from what Shesha was mentioning before about contribution from India. I think India could be the next IBM if they start, or if you think in that way, that you make a new quantum computer, you produce your hardware, you produce your software, then you can be a next IBM. You don't need to work for IBM.
Yeah, that's the entrepreneur fever that can get into all these verticals, be it photonics or be it.
Well, you see, at the end of the day, it's manpower. It's the human brain that actually works. It's nothing else.
Yeah.
And that needs a support from the government as well, and also the kind of ecosystem that you would build up in there. It's not easy, but it is possible.
And continuous flow of money, funding, and then the synergy between industry, academia, and startup.
Well,
and things
it all means a long-term planning. Yeah. So it's not that you just do it for a day and then stop it. Yeah.
Yeah, so maybe in 30 seconds, if Shesha and Nithyasri can add their points, just one or two punchlines.
So in my view, I think building hardware, or I don't think it should be an either or. India is big enough country with large enough economy to handle all of that. I never meant it as either or in any case. But I think where we need to be now look at in the current Indian context is education. In the broader sense of the term, across the board. And in the last few months, you won't believe the kind of, so many people are reaching out to me for conducting sessions in different universities, different things. There is a big interest. Just as a reference point, just last year, we conducted a code challenge, and we were looking at roughly 1,000 people or so for that coding challenge. It got over within 1 hour registration, and then we had to close it down.
All these hackathons and
such. This was India-specific hackathon that was done last September, and we had to close it down within an hour because of the amount of registration we had. So there is some at the students level, they are very smart with the internet and everything. They know what's happening and so forth. They want to learn these things. There is a lot of desire. I think now there is a gap in terms of universities and the education system not providing that systematically. I think that's where the next challenge will be.
To address her point in just 30 seconds, if I were to ask you, so what are the key challenges for the startups? How many startups in quantum area are there in the country, and where do you see what is required? Support from the government and industry.
Yes, absolutely. Regarding the support from government, we are getting a lot of support, and I totally agree with Professor Manas. And India can become the next IBM, and that is because I would like to say two things. The government has allocated $1.12 billion for quantum computing research in India. And just recently, our Prime Minister, he had a summit with the Prime Minister of Finland, and their main point of discussion was quantum computing. And I'm very happy that India is marching forward to become one of the leaders in quantum computing. And now the challenge is...
How many startups are there in India? How many startups are there? Quantum startups are there in India?
There aren't much. I wouldn't say that.
How many? If you could throw a number at me.
There should be 4 or 5. There are some in Bangalore, and but I don't think they are very large scale and not in the global perspective. When you look at it, we have a long way to go, but we have the funding and the support for it.
And figure out the right kind of technologies to get those enablers right. I think this is great. I think I'm sort of 1 minute off. It's 18:31 hours. So therefore, it was very interesting to be part of this panel. So to summarize, I think quantum technologies, quantum science, getting into technology, and that folding within the AI is going to be really, really powerful. And India is rightly poised, along with the rest, the top countries and players in this field. And it requires, India has the manpower to go ahead with it, and you have the infrastructure with the support and synergies from the government, from the industry that can propel and fuel startups. I think we could be, it could make waves, is what I foresee, right? And so this, in a summary, summarizes, and I think there are a lot of exciting research areas, and I'm sure we can have an hour or maybe even 2 hours of discussions, but to cut it short, I think this is a really exciting time to be working in this field. So I again thank the panelists, Manas, Shesha, and Nithyasri for their views, opinions, and candid thoughts on various aspects. And I thank the organizers for this wonderful session. So with this, I would like to conclude.